for the introduction. I hope you can hear me. I'm Mauro Pezze from the Università della Svizzera, Italiana in Lugano, and from Schaffhausen Institute of Technology in Schaffhausen, both in Switzerland. I present work that I did with Rui Xin, who was my PhD student at Università della Svizzera Italiana, and he's now in Amazon Japan in Tokyo, and work done with Leonardo Mariani and Oliviero Riganelli from the Università degli Studi di Milano-Bicocca. The work is about predicting failures in complex systems, and so it's about runtime failures. And I like to start by stressing that runtime failures are unavoidable. Here I have a quick essay of few cases of software failures who actually made the news. So for the amount of disaster they provoke, I also have some data, fairly small data, by the way. So I have like data from different agencies. The average downtime per year is expected for application which are 24/7, about 10 hours. The cost of an unplanned application downtime per year is about $2 billion, and the average cost for a critical application failure per hour is about $500,000 to $1 million. So we're talking about a relevant problem, and what we can do is we can actually address the problem by predicting the failure. So given that no matter how good we are in building the software, how good we are in testing the software testing or software programs can fail, a good approach is to actually try to predict failures at runtime. So you monitor the system, you predict the failure, you locate the fault, and you execute the fixing to avoid or mitigate the runtime errors. Today, we're talking about a new technology to predict failures in complex systems. Predicting failures is not new per se. There are several approaches. There are approaches called anomaly-based approaches and signature-based approaches. Anomaly-based approaches identify anomalies, which means behaviors that deviate from the normal system behavior. They suffer from false positives because once the behavior that deviates from whatever has been acknowledged as a normal system behavior, it's difficult to say whether it's just an exceptional situation or it's a fault symptom. Signature-based approaches work with signatures. They refer to computers to fault signatures, and they actually work on known patterns of failure-prone behaviors, no false positive, very few false positive, but limited to known failures that meet the patterns that are already known. So in both cases, we have some severe limitations that we try to overcome with our approach, which is called premise, which makes together anomaly-based and signature-based approaches. We focus on multi-tiered distributed systems, which means basically the vast majority of complex systems, say cloud system, for example. And we merge anomaly-based techniques, in particular Granger causality and time series analysis, with a signature-based probabilistic classifier to get a few false positive and predict anomalies beyond the limit of limit of known patterns. And we also, of course, use a fault seeder to actually train the system. The application or the approach is as expected based on two different phases. There is an offline training phase and there is an online training phase. In the offline training phase, what we do is we build the models that we use later in the online training phase. We build a baseline model and we build a signature model. We build a baseline model with two steps. We look at univariate anomalies. So we monitor the system, we monitor a matrix of the system at different nodes. We monitor key performance indicators, KPIs. We monitor many of them, and we actually track the behavior of the system for quite a long time. And we build a confidence interval so that we actually know when the behavior is out of this confidence interval. Then we get anomalies univariate, referring to one single KPI. And then we actually use Granger causality to build the causality graph where we actually try to identify the causality relationship between different anomalous values. And in the graph, we have the KPIs that represent the nodes, And we have the edges which are marked or that are annotated with a causality, with a probability that indicate the probability of the causality relation between the two nodes. Then we have a second element. We build also a signature model. We build a signature model using classifiers trained with injected faults. So in the first phase, we use Granger causality trained with normal executions only. In the second phase, we use signature models trained with injected faults. In these injected faults, we actually tried different kind of classifiers. We tried the support vector machines. We tried Bayesian networks, best path, first decision trees, naive Bayes decision tables, logistic model trees, and hidden naive bases to see which one was the best. We report the results later on, but in general, we found a sort of fairly stable and well understood classification of behavior of the systems. And so at this point, we move from the offline prediction. So offline prediction training systems, we actually build a baseline model and signature model. We use this model in the online prediction. Online, we monitor the system execution. We get the same KPIs. So we get values of KPIs, and we do detect anomalies with time series analysis. So when we talk about monitoring KPIs, what happens is that we monitor KPIs for a given time intervals. Every time interval, a fixed time interval, we get a set of values, one for each KPI. So we have a time series of set of values for the KPIs, and we do several steps. First, we look at anomalous single anomalous KPI, single anomalies, univariate anomalies. This is happen when you have the system that goes out of the range with respect to the model we built in during the training. And then we actually move that and we use the Granger causality graph to identify the different kind of the relation between the causality relation between the KPI that are anomalous and the probability of this relation. And so we end up with a time series of anomalous KPIs grouped according to the Granger causality relation. Okay, so in the example, we actually see it at different time steps, T1, T2, T3, T4, and so on. At some point in our execution, we actually see some anomalous KPI, and the patterns can be very different. The one that is shown in the example is actually a pattern that we revealed in our experiments. And we look at a window, a time window of the series, because we cannot elaborate the full window. And what we do is we actually get the different KPIs that are ranked according to the Granger causality graph and grouped the Granger causality graph for each timestamp. And at each timestamp, we feed the anomalies aggregated according to the Granger causality graph to the classifier. And here we see the example of as an example, the support vector machine. And we use the support vector machine to try to move from the prediction of a failure somewhere in the system, we call a general prediction, to the prediction of the failure in a specific system, which is what we call a specific prediction, which means basically we are able to localize the node or the cluster, which is the failures and the type of failures. And we did actually evaluate this with a set of experimental settings. Okay, we used as a test bed a local cloud system that we actually installed. The local cloud system is composed of 8 servers where we implemented a full chain of system. We actually have OpenStack, Ubuntu, KVM hypervisor, and we have Clearwater running on top of the system. And Clearwater, for the one who are not aware of, is a typical system that is used in telecommunication applications to experiment with different kind of cloud systems. We injected the different kinds of faults. So we injected faults, packet loss, memory leaks, CPU hogs. These are the type of faults that are the most frequently observed in systems like Clearwater. We injected faults with different injection patterns. We went through linear, exponential, and random patterns, and we collected key performance indicators, KPIs, at application, AIS, and OS first operating system level. We collected over 600 KPIs per time step, and we ran over 680 execution, all possible combination of seeded errors and patterns and normal executions, each one lasting 2 hours. So it's a big amount of experiments, and we use the data collected in the experiment to understand whether the approach is reasonably it's reasonably better than the former approaches. We started first by evaluating the size of the sliding window. I hope you still remember that we do time series analysis on a window, which is a sliding window over time. We evaluated different sliding window size, 60, 90, and 120 minutes, which are appropriate for the sample rate that we use. And we experimented with all the probabilistic classifiers that I mentioned before, and we got very, very consistent and good results. SVM performs slightly better, so we ran all the other experiments with SVM, but I'm sure that other systems could have to be used as well. Then we try to actually understand what is the effectiveness of the approach in terms of ability of predicting failures and locating faults. We did actually run the system once trained with different injected types, fault types, with different injected patterns, and we actually measured precision, recall. We computed the F measure, we measured accuracy, and we measured false positive rate. The numbers you see are ranges because we actually repeated the experiments with different patterns for the same fault type, and we repeated that several times to get the statistical evidence. You see that we have a very high precision that depends on the fault type, which as expected. We have a very high recall, again, depends on the fault type. We have a high F measures, very good accuracy. What actually was really, really good is the false positive rate. We got a false positive rate, which is extremely high. We got only 74 false positives out of over 4,700 window samples. That's one part of the prediction. So I think, you know, the data gives us evidence that by combining the two approaches in a good way, the way we do, we get a very good, very effective system. But predictions are useful only if done early enough. So in our time frame, we have 4 different timestamps. We have what we call fault occurrence, you know, in our experiments, when we first see the fault, so when we actually have the system that is perturbed due for the failures. And then we have the system failure, which happen quite a long time after they start seeding the fault. Of course, you know, if the fault is actually immediate, it's difficult to predict anything, but in most cases, the failure happens to be after a while, after the fault has been started manifesting. And then we have 2 events, which is what we call general prediction, which is when the system tells us that there is a possible faults, incoming fault, and the failure specific prediction, which is when the system tells us that the fault is located in a given node and is a given type. Working with seeded faults, we can actually see whether this is a good or bad failure specific prediction. And what we do is we have 2 time windows, which is the time to prediction and the time to failure. The time to prediction is the distance between the time we first see the faults and we predict the failure, general time to general prediction, and we predict and locate the failure, time to failure specific prediction. The shorter the time to prediction is, the highest, the earlier we can know that the failure will occur, and so we can take action. The second time frame is time failure. Time to failure is the time that goes from the prediction to the system failure. 2 time to failures from general and from failure specific prediction. The bigger the time to failure is, the more time we have to actually deal with the failures. We did report this for every, we compute that for every kind of fault. Here is are the full data. Okay, what we see in this is the time to failure, so the time to prediction. So it is the time that goes from the fault injection to the fault failure prediction. TGP, time to general prediction, which means how much time it goes from the time we inject the failure, the fault, to the time we actually have a general prediction. This varies from 5 to 65 minutes. We work with samples of 5 minutes, so it actually we can make the first prediction right to the next sample, in the best case, in no more than 13 samples afterwards. Then there is the time TTFSP, the time to failure for a specific prediction, which is not only when we actually have a general prediction, but we already located the fault and the type of fault. And this goes from 20 to 80 minutes, which means from 4 to 16 samples. Good results, which are getting even better with the second part, which is the from failure to failure prediction to failure, which is the time that goes from the time we actually predict the failure to the time the failure actually occurs. And in this case, we also have the from general prediction to failure and from failure specific prediction for failures. And we have different ranges. From general prediction, the range goes from the worst case of 48 minutes to the best case of over 12 hours. Over 12 hours means that we know that the system will fail because we injected the fault, but it did not fail for the following 12 hours. We see that we do have more than 45 minutes in any case from the general prediction, and more than 20 minutes from the failure specific prediction to actually act, which means we have quite a reasonable time to figure out what's wrong, and quite a reasonable time to figure out at least what is an immediate act that we can take. For example, micro reboot or rescheduling the task for a sort of tentative to actually reduce the things. So excellent results. Two major limitations. We train with injected faults, and our customers, industrial customers or industrial interest who work with 24/7 systems say it's difficult to actually inject failures in systems that actually work 24/7. Other thing is a long training time. You know, we work very well on stable systems, but we don't work well with dynamic cloud systems. So this work has been published this year. It has started a long time ago, and between the submission and the publication, we did other work. And so I want to conclude this presentation with 2 pointers. Okay, we did work on these 2 major limitations. We did actually work on the limitation of training without injecting faults, and we have been modifying the system. We now have a new system that actually can work, puts together Granger causality, time series analysis, and graph theory, and centrality measures, page ranking, and this is working without injecting the faults during the training phase. We published the result and presented the result at ICST 1.5 years ago, and we get similar results, but without the limitation of needing to inject faults during the system training. Then last slide, we actually also worked on the problem of adapting to long-lasting, highly dynamic systems, and we've been experimenting with easing free energy, which is a model which has been successfully important from physics in many different cases. And we worked with implementation with RBM, restricted bottom machines, and also we presented the results at ICSI last ICSI, the new ideas and emerging research track, and at ICST, and the results are pretty good. And with that, I let you actually open the time for question and give back the word to you all. Thank you for attending this presentation.
Okay. Okay, thanks. Thanks to Professor Pezze and for your excellent sharing. And I see there's a question in our session Q&A. What type of system are you talking about? Was it evaluated with an industry partner?
Yes, thanks. Sorry, I didn't see the question on the system. Anyway, thanks for repeating the question. Yes, yes. This work started with a sort of our interest. So the type of system we actually used are multi-tile system, cloud systems. So we actually have been working with several different industrial partners. There is also an industrial implementation of this system. There is a commercial product that implements this system. And we're working right now with a new partner. So we've been working with three different partners: a large telecommunication company, a company that is a software company that work with industry automation, and now the company that works with cloud frameworks for safety and security issues. And we do have results also in the new papers that we are working on now, on large experiments with system running on industrial settings.
Okay, thank you. So I have a quick question. Actually, I got questions about the failure types and the fault types. So according to your presentation, the failure type in the anomaly tuple of the signature model are in terms of the harmful or benign, right? If I'm not misunderstanding.
Yes.
Okay,
let me actually give you a sort of a framework. Maybe I can actually give you a framework, and then you can actually maybe see where I can address you properly. Okay, this is a big issue. You know, what kind of failures you actually train the system with, what kind of failures you actually experiment with, and in this paper, we report results for a system that actually is trained with injected faults. So obviously, our results are bounded to that kind of faults. In general, if you actually evaluate the system injecting a given kind of fault, you know, you actually get the results of that kind of faults. And I presented in the slide, actually, the faults depend on the results depend on the kind of faults, so you don't get the same result with the same kind of faults. We selected the failures to inject according to our industrial partners. So we went to the telecommunication company, and they tell us this is what you want. A good example is, for example, packet loss was a big priority for telecommunication companies. That's a very, very important fault that they cannot avoid at runtime, and they ask us specifically to report on that kind of faults. We also selected faults that actually are the most common faults as reported in questions. We are now moving on with the company working in the area of security, and we are injecting security-related faults in the moment. Also, of course, the limitation is we need to have a good fault injector, which is not easy to implement. I hope I addressed your concern.